Hello and welcome to the first video lecture on the topic of compound stresses and strains. Now in the previous topics that we studied about stress and strains, we were dealing with either a pure normal or direct stress, either in tension or compression, or a pure shear stress. Okay, so either we had a pure compression or tension, or we had a pure shearing. But in most of the cases we have both direct stresses and shear stresses. This means both of them are acting at one single plane at a particular instant of time. For example, if you look at this section, on this section you have tau also and you have sigma also. Now due to both of these you will have a resultant stress acting across this plane. Now let us say sigma is your direct stress, tau is your shear stress, then sigma r would be your resultant stress. Now sigma r can be given to be under root of sigma square plus tau square with the help of Pythagoras theorem, and phi is the angle which is between the normal to the plane and the resultant stress axis, and this can be found out by tan inverse of tau upon sigma. In this chapter we would be going through these 6 topics. You would be studying a body subjected to simple tension, a body subjected to pure shear, then you will have pure normal stresses, you will have generalized 2D stress system, you will be talking about principal planes, and then we will be talking about the Mohr's stress circle. Now point 1 and 2 will be discussed in this video lecture, that is video lecture 1 on this topic. Topic 3, 4 and 5 would be discussed in the video lecture number 2 of the chapter, and number 6 would be discussed in the last video lecture. Starting with the first topic, that is a body in simple tension. Now you have a bar, let us say this is the bar that in question, this is the bar in question, this is any section of the bar. Along its length it is being subjected to a direct tensile stress sigma. Now across any transverse section, that is a section like AB, the stress would be only sigma. Okay, but what if at an oblique section AC? Now across this you will have again two components, that is sigma tau theta, and then one will be perpendicular, that is sigma theta. This means when we talk about oblique planes, on oblique planes you have a stress which is acting along the plane and a stress which is acting perpendicular to the plane. Now due to these two stresses acting simultaneously, you would have a resultant stress that comes into picture. Now if you redraw this section over here, you have A, B and C, and AC being the oblique plane. Across this plane, along this plane you have stress tau theta, and perpendicular to this plane you have stress sigma theta. Let us say the complete you just create it in the form of an element. Let us say the bar thickness is T, so this thickness would also be T. Okay, so what is the force on the body? Force on the body is stress into area. So if I have to find the stress in the perpendicular direction, this would be stress into area. Area is how much? Thickness into AC. So this would be AC into T. And what would be the stress along the plane? That would be stress AC into the same area, because this is a shear stress, and shear stress always acts along the surface, so you have to take the surface area. Now there is one more stress which is acting, and this stress is sigma. Now sigma is perpendicular to this plane, so the force acting on this plane is stress, that is sigma into the area of the plane, which is AB into T. So these are the three forces which are acting on this element. Now if we draw these three forces, let us say this is the horizontal line. Okay, this is sigma AB into T. This is tau theta AC into T. This is angle theta, and you have a line which is perpendicular to tau theta, that is sigma theta. Okay, AC into T. Now our aim is to basically find out sigma theta and tau theta that are acting on the oblique planes. Now to find them, we would have to resolve this force, that is sigma into AB into T, in two directions. One direction would be along this, and one direction would be along this force. Let us first resolve this force along the direction of this force. Okay, now if I extend this line like this, if this angle is theta, then this angle would also be theta by basic geometry. Okay, because the angle between this line and this line is theta, so the angle between the line perpendicular to this line, that is this, and the line perpendicular to this, that is this, will also be theta. If I resolve this along this line, this would give me sigma AB into T AB into T cos of theta. Sigma AB into T into cos of theta. This means I can write down sigma theta into AC into T. This is equal to sigma into AB into T, sigma into A into B into T cos theta. Now if I find the value of sigma theta from this, bring this AC in the denominator, so you would get sigma theta as sigma into this T, and T would cancel out. You would have AB by AC into cos theta. Now if you look at this triangle, you have AB, that is the base, upon the hypotenuse. So cos theta is AB upon AC. If I substitute the value of cos theta in this equation, the value of sigma theta would come out to be sigma cos square theta. So this is one value that we were hoping to find out. The next step was to find out tau theta. Now tau theta, I told you, is would be found out when we will resolve this force along this direction. Now let us extend this line backwards, and we resolve, take a component of this along this. So this will be a component of this force. That would be sigma AB into T sine theta. So this force is equal to this force. Now if you equate them, we would get tau theta into AC into T. This becomes equal to sigma into AB into T into sine theta. T and T are cancelled out. AC would go on to the other side, so tau theta would become sigma into sine theta into cos theta. Now if you divide it by 2 and multiply it by 2, this would become sigma by 2 into what is 2 sine theta cos theta. This would become sigma by 2 into sine 2 theta. So these are the two values that we were hoping to find out, and we have found these out. So you have the value of tau theta and you have the value of sigma theta. Now what is the value of sigma r? That is the resultant. The resultant we found out was sigma theta square, just a minute, sigma theta square plus tau theta square. Now if you plug in this value and this value in this equation, you would get the value sigma cos theta. You would get sigma r as sigma cos theta. So you need to remember this value, that the resultant stress for a system which is just having simple tension in it will have sigma cos theta on any oblique plane, and sigma theta would be sigma cos square theta, and tau theta would be sigma by 2 into sine 2 theta. Now if you look at this value again, according to this, if theta is 0, you would at that time have the maximum value of normal stress, okay, and that would be but obviously equal to the applied stress. If you look at this value, if your theta becomes 45 degrees, then the shear stress along the plane becomes maximum, okay, and it becomes equal to the half of the applied stress, okay. So at theta 45 degree you have maximum shear stress along the plane, oblique plane, and at theta 0 degree you have a maximum normal stress on the oblique plane, okay. So this was about the topic of a body subjected to simple tension in a compound stress strain system. Moving ahead, let's look at a body which is subjected to pure shearing. Okay, so this is the body which is subjected to pure shearing. There is no tensile or compressive stress acting upon it. You have a shear stress along this that is tau, and you have a shear stress along this plane, that is tau again. Okay, now how do we solve this? Again, at an oblique plane, that is AC, at an angle theta to the transverse plane AB, you have two stresses acting, sigma tau theta and sigma theta. Now how do we solve these equations, or how do we find out the value of sigma theta, and how do you find the value of tau theta in this case? Now the value of sigma theta in this case, just remember it for the examination point of view, is tau sine theta, tau sine 2 theta, sorry, and the value of tau theta in this case is minus tau cos 2 theta. Now a point to understand this is the negative sign. Originally we assumed that the shear stress in the upward direction along the plane, but due to this assumption the value has come out to be a negative value. So the actual value is like this. So your resultant is in this direction. Okay, so this is how it takes place, or this is what happens in this. Okay, so this is quite simple. Now if you go down in this slide, you will have a look at these two figures. Now this is the original figure that we have. You have tau acting here along these faces. Now what happens if you tilt, or if you take a plane which is at 45 degrees to this plane? At a plane which is at 45 degrees to this plane will be a stress sigma, which will be numerically equal to tau. Okay, and perpendicular to this plane you will have another plane on which there will be stress acting sigma, and that will be again numerically equal to tau, but both these stresses will be opposite in nature. Okay, so this means that at the point where you have a pure shear stress condition on two given planes, let us say this and this, okay, the action across the planes of an element taken at 45 degrees to the given planes is one of equal tension and compression. Okay, so if I take this point, at this point I have these two pure shearing stresses being applied upon. So if I go 45 degrees to these planes, okay, on those planes that are at 45 degrees, you will have simple tension and simple compression, and they will both be equal. Okay, the main thing is to remember this point. It is quite easy to remember these formulas for the given case, but the main thing is to remember these points. That is, if you tilt it by 45 degrees, the stress becomes one of tension and one of compression, and both are equal and equal to the shear stress that is being applied onto the body. Okay, now in the next video lecture we would study about the remaining three cases before we move on to the Mohr stress circle. Till then, have a good day. Bye bye.